Broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, and welcome back to the Green Chemistry Education webinar series hosted by the Green Chemistry Commitment. Thank you for joining us and our speaker today, Dr. Paul Richardson, for the Tools for Innovation in Chemistry from the ACS GCI Pharmaceutical Roundtable webinar. My name is Natalie O'Neill, and I'm the Program Manager at Beyond Benign, a nonprofit organization dedicated to green chemistry education at the K through 12 and higher education level. This webinar series is designed to highlight relevant topics in green chemistry education for faculty and students looking to adopt green chemistry in their courses and programs. Sorry, there, just a little issue with changing the slides. Today's webinar is co-hosted with the ACS Green Chemistry Institute Pharmaceutical Roundtable, which is one of the industrial programs of the ACS Green Chemistry Institute and the leading organization dedicated to catalyzing the integration of green chemistry and engineering in the pharmaceutical industry. We are broadcasting live and recording this session. Therefore, attendees are in listen-only mode and all lines are muted. If you have questions, please type them into the chat box or the question box on your control panel for one of our moderators, either myself or Dr. Izmir Martinez, the manager of the Scientific Alliance and Business Engagement for the ACS GCI, to monitor. We will respond to any questions we can after the presentation. The recording will be posted on the link you see in the welcome box and on this PowerPoint slide. Any supporting documents, such as the presentation slides, will also be posted at this link as well. For those of you who participate in social media, please connect with us on Twitter or Facebook. We would love to hear some live tweeting going on during our webinar. So join us in if you would like. If you are joining us as part of a class, department meeting, or an event, please let us know in the chat box or on social media so we can acknowledge your group's attendance. Thank you for joining us for this webinar and taking part in this discussion. This webinar is being brought to you as part of the Green Chemistry Commitment Program, which is a consortium program aimed at transforming chemistry education, expanding the community of green chemistry practitioners, growing departmental resources for those looking to adopt green chemistry, improving connections to industry, and effecting systematic change in chemistry education. This program is voluntary, flexible, and it's looking at programs for adopting green chemistry through steering learning objectives and for promoting the work that you are currently already doing at your institution that can serve as a model for other institutions to get involved with green chemistry. You can find out more information on the link provided here on the slide, or you can email me directly. As always, as part of our webinar, we're going to be doing a green chemistry swag giveaway. We will be randomly selecting a winner from the webinar attendee list. We will announce the winner at the end of the presentation and contact you after the webinar concludes to send you one of the following of your choosing. So on the slides, you can see we have a green chemistry t-shirt up for grabs, a real-world case study in green chemistry textbook, and also the Green Chemistry Theory and Practice book by Paul Anastas and John Warner. We are happy to have a wonderful webinar for you today on the tools of innovation in green chemistry from the ACS GCI Pharmaceutical Roundtable. So now, just to introduce our speaker, Dr. Paul Richardson is currently the Director of Analytical and Synthetic Technologies within On-Call Medical Chemistry at Pfizer in La Jolla, California. Paul joined Pfizer in 2004 after working with Lexicon Pharmaceuticals in New Jersey as the Director of Process Chemistry for 8 years. Paul received his PhD in Organic Chemistry from Sheffield University, where he worked with Professor Easton Marco. Paul completed his postdoctoral research studies at both Exton University underneath Professor Stan Roberts and at Scripps Research Institute. Paul is a member of the American Chemical Society and a current co-chair of the ACS Green Chemistry Institute Pharmaceutical Roundtable. Paul is an author of over 200 patents, papers, reviews, and book chapters, and we are so thrilled to have him here today to present the tools of innovation. With that, I'll give the controls over to you, Paul, and I will let you take it away.
Cool. Thanks, Natalie. That was a very kind introduction. I'm not quite sure I'm worthy of that sort of introduction, and hopefully this will go well. Okay, so here's my first slide, a quick introduction of what I'm going to talk about today. I'm going to talk about the tools for innovation developed by the ACS Green Chemistry Institute Pharmaceutical Roundtable, or the ACS GCI PR. Of course, we have to have many acronyms because we are the pharmaceutical industry. The structure of the talk, what I'll do today is I'll briefly give a quick introduction to a little bit of green chemistry, which probably isn't necessary for this audience here today. I'll talk a little bit about the roundtable, the work we've been doing over the past sort of 15 years or so, and then I will take you through some of our tools and try and introduce them and sort of try and point out their utility, not just in industry, but also in academia as well, to sort of promote and encourage people to adopt green chemistry practices. So this is the first slide. It asks the question, why green chemistry? And you might say green chemistry is one of these things that it's an absolute win-win when you sort of look at all the things like good for the environment, you prevent waste, etc., etc. But you know, sometimes, particularly in the pharmaceutical industry, where there's sort of time pressures, and there's always things like, you know, you only have a certain patent life on a compound, there are sort of people who can make counter arguments to say that you don't really have time to adopt green chemistry. But this is kind of a couple of sort of definitions of why green chemistry. One is to provide the best efficiency for a chemical process. It's a great opportunity for innovation, a new frontier of exploration. But one thing that I think really sort of resonates within industry is the achievement of getting superior synthetic efficiency will ultimately deliver a competitive advantage. And what I'll sort of show throughout, try and demonstrate throughout this sort of presentation today, is the fact that, you know, green chemistry is also a more economical way to sort of to do your chemistry. And once you start bringing economics into the discussion, then you really have a very, very tangible driver in terms of having people adopt green chemistry practices. Okay. So, sorry for that. In an attempt to encourage Natalie's push for the swag giveaway, I thought I'd sort of do the 12 principles of green chemistry, and you can find these in the Anastas and Warner book that was part of the sort of as I say, swag giveaway. What it sort of is, these were introduced in the late 90s by Paul Anastas and John Warner. But one thing I sort of wanted to focus, and the reason why this sort of circle thing is color-coded, is the principles don't just encompass the process, they also encompass the starting materials and the product as well. As you see, the two circles shaded in red here refer specifically to the product in terms of you want to design things to degrade, and you also want to design benign chemicals. But the one thing is, all the ones focused in green focus on actually how you do your chemistry, sort of real-time analysis, doing catalytic reaction, using benign solvents, and obviously the safety of the process itself. So really, this is a kind of a roadmap to sort of how people do chemistry. It's very easy to sort of say in pharma that you should adopt the 12 principles of green chemistry. But a couple of years ago, there was an editorial from folks at Amgen, and specifically John Tucker and Margaret Fall. And this came out in quite a prestigious journal, Nature. And what they sort of did was they took something known as the triple bottom line model, which was introduced as a sort of a roadmap for an industry to be successful. And what that sort of model looks at, it says for an industry to be successful, you have to be successful in how you deal with your people, you have to make a profit, and you also have to sort of be environmentally sustainably responsible in terms of how you do the planet. And sort of this editorial finished off with, you know, it sort of looked at the green chemistry principles, and then it sort of linked each of them to how they affected people, planet, and profit. And right at the end of this, there was this quite strong statement right at the end of the article saying that green chemistry obviously can deliver for people, planet, and profit. Those who embrace it will reap the benefits in the future. And then this kind of striking phrase, those who fail to evolve may cease to be relevant. Okay, so switching gears a little bit and sort of introducing the Roundtable. The Roundtable, Green Chemistry Institute Pharmaceutical Roundtable, ACS, was created in 2005 with 3 member companies. I believe it was Merck, Lilly, and Pfizer. We're now up to over 30 members. I believe it's 34. You'll see all their logos on the final slide. So what's kind of the real driver for sort of green chemistry in pharma today? Okay, so overall, these numbers are from a book by BuzzQ, published in about 2012. Pharma and generics produce 100 million kilograms of active pharmaceutical ingredients per year. Okay, for each of those kilograms, basically, to make an API, it was estimated you have 150 kilograms of waste. So that basically comes out as sort of 15 billion kilograms of waste per year. These are pretty big numbers we're talking about. But what I think is, as I say, is a number that will more resonate sort of when you try and adopt green chemistry in the workplace is the estimated cost to dispose of that waste is $30 billion. And that obviously impacts a company's bottom line. On the left-hand side of the slide in the green boxes sort of show the strategic priorities of the Pharmaceutical Roundtable. We aim to inform and influence the research agenda. We aim to promote education and training, enable global collaboration. As you all know, probably the pharmaceutical industry collaborates across the world now. We have outreach efforts both in China and India. And what we're here today to talk about is to define and deliver the tools we use for innovation. Now, I just want to say that the Roundtable has been around. Next year will be our 15th anniversary, and this slide is a poster from our 10th anniversary celebration. And what this aims to show is, I realized sort of we had to do a webinar today, and then I, didn't just go away and sort of try and think up like a couple of tools to present in the last week or so. We've been actively involved in sort of delivering these tools over the whole sort of evolution of the Roundtable up to this day. And what you'll see circled in red here are the tools we're actually going to talk about today. You'll see Process Mass Intensity Calculator around 2009, a Solvent Selection Guide in 2011, and then more recently our sort of Convergent Process Mass Intensity Calculator, and then our Reagent Guide. One very exciting development for the Pharmaceutical Roundtable this year was we sort of rolled out a new website. Now, one thing is very important, as I say, in the industry, is you have to know your acronyms. Our website address is www.acsgcipr.org. I'd actually probably bookmark that because trying to remember it can be a bit of a mouthful unless you know what the acronym kind of stands for. It's a great website, a lot of really useful information there. But what you'll see is when you go to the front page, you'll see these 4 boxes which I presented on the previous slide. And if you click on these, it'll bring you to tell you more about each of them. And as I say today, we're going to talk about tools for innovation in chemistry. Okay. Go to that page, Tools to Innovation in Chemistry. What you'll get is you'll get a laundry list introducing why we started developing tools into sort of the late 1990s in the pharmaceutical industry to sort of make the implementation of green chemistry in the industry more simple to adopt for sort of workers, scientists at the bench kind of thing. On this page, it will then sort of go through the various tools which we have, which I've listed on the right-hand side. The ones we're going to talk about today are highlighted in green, as I say, the PMI Prediction Tool, Reagent Guides, and Solvent Tool. But there's also, a load of other good stuff here as well in terms of like medchem tips and tricks to help out your chemistry. There's a look at sort of life cycle analysis with the PMI tool. There's a green chemistry innovation scorecard calculator, and more recently we've started looking at sort of the greening of analytical chemistry, sort of what methods of purification and sort of preparation of samples and analysis are important and how to make them green. So as I say, we're going to talk about 3 things today, and this is going to shown on this slide here. We're going to talk about everybody's favorite topic, metrics, as I say, PMI, process mass intensity. We're going to talk about solvents, and we're going to talk about reagents. Now, I wasn't just happy to sort of put these pictures together. I was, kind of quite proud of my sort of clip art abilities to find pictures to represent each of these things. But I think the 2 on the right-hand side sort of represent something quite important. Solvents are, as we'll see later, are a huge sort of burden in terms of usage in the pharmaceutical industry, and it's always very important to consider them. Reagents, as you'll see on the right, they come in many shapes and sizes. Obviously, sort of with the principles of green chemistry, we want to adopt doing catalytic reactions. But again, it's sort of very important which reagents you choose because they all sort of have different sort of impacts. Okay, so I said metrics are everybody's favorite topic. So the question that a lot of people sort of ask is, well, why do you want to sort of look at metrics? And I'm trying to advance the slide. Sorry. Natalie, can you advance the slide, please? Okay, So why do we want to look at metrics? I know this is everybody's, least favorite topic on the planet. Unfortunately, unlike, fantasy football and fantasy baseball metrics in chemistry are probably not as exciting. But really, there are absolute drivers to do this. It's very useful to sort of come to your end of year review or look at your process chemistry and say, well, I did the chemistry, I adopted the principles of green chemistry, and it's a very green process. But that's just a very sort of qualitative statement. There's nothing to actually quantify what you do. You can't really manage what you don't measure. As you say here, we measure what we care about, so we care about what we measure. Also, the standardization of measurements of a chemical process greenness allows benchmarking across the board. One thing that's absolutely critical, and we'll see there's a real sort of gamache of metrics out there, the proper choice of metrics is critical to evaluate the behavior of a system. And as I said, the one thing that's sort of really, I hope I can demonstrate today, is green metrics do correlate to actual process economics. So basically, metrics have been around for forever. And this is a kind of a look at some of the initial metrics. On the left-hand side is the famous chemical yield. As a grad student, everybody's favorite yield is greater than 99%. It's very exciting to get a high yield. It's a very, very good sort of warm feeling inside. This is probably my biggest problem with sort of the introduction of electronic notebooks, where it's sort of calculates the yield for you, because now you kind of find out if you don't sort of purify your reaction or you carry on sort of crude product, you start to get yields like 150% yield. And unfortunately, that doesn't get you very far because nobody believes you. And if you are creating matter, then I'd be expecting a call about the Nobel Prize. However, the pharma average is usually about 86% per step, so we're actually doing pretty well there. But the one thing about yield is what you're doing is you're just looking at how much product you get based on a certain start material. You're not capturing all the materials you used. Introduced in the early 90s by Professor Barry Trost at Stanford University was the concept of atom economy. And the way I kind of look at this in terms of is how many atoms of your starting materials actually end up in your product. It's a pretty good metric. It's actually the one that's used in the principles of green chemistry in terms of, a focus on an atom economy. But again, there's sort of a downfall here in terms of you're not considering everything that's going into the process. You're not considering the reagents involved. For example, sort of when you look at doing a Mitsunobu reaction, it's a great reaction in terms of atom economy, in terms of product and start material. But when you're ignoring like two reagents like triphenylphosphine and an azodicarboxylate, you're missing a lot of materials that are in the pot. On the right-hand side is a metric introduced by Roger Sheldon from the Netherlands, the so-called E factor. And what that calculation is the total kilograms of waste divided by the kilograms of product you get. So now you're actually looking at how much product you get based on sort of how much how much waste you generate to generate some product. Down on the bottom left-hand slide is a table that Sheldon actually included in his initial sort of paper on the E factor. And this is one that sort of really, I think, resonated with the pharmaceutical industry and to some degree, was a driver towards people taking a more closer examination of green chemistry sort of in the sector. What it sort of looked at was a various industry segments: oil refining, bulk chemicals, and fine chemicals, looked at how much they produce per year, and then sort of did a sort of an analysis in terms of what their E factors were. And as you could probably see, highlighted in the red box, the pharmaceutical industry didn't come out very favorably. Okay, so when I say this, there was three metrics, all of a sudden there's an absolute explosion in terms of how many metrics are out there. And I'm not going to go through them all in this table, and trust me, there are even more. But you can see at the top the three we just looked at: the chemical yield, atom economy, and E factor, and also sort of the process mass intensity, which we're going to discuss. But what this sort of traffic light representation is intended to do is look at what sort of inputs and outputs these metrics actually take into account. They all, some of them take into account waste, yield, some take into account the stoichiometry of the reaction, but the two most important factors that I sort of like to focus on here is the solvents and water used in the process. As you'll see, chemical yield, atom economy don't consider these to any great degree. And the next slide is actually going to show, how far off base you're going to be if you don't sort of take into account how much solvents and water you use in your process. This is from a paper in 2011, actually from the Pharmaceutical Roundtable. And what the sort of pie chart, a rough pie chart shows on the right-hand side is actually how much solvents and water contribute to a process mass intensity. Solvents contribute 56%, whereas water, sort of aqueous washes after the reaction, etc., constitute 32%. Compared to reactants, reagents, this is, you know, greater than 85% and is the vast majority. Obviously, the thing here is you need process intensification, solvent recycling is important to reduce the amount of solvent waste, but it's also key once you sort of do your calculation in terms of process greenness, or you do your benchmarking, that you absolutely want to include these two elements, the solvents and the water. And that's why we sort of look at the process mass intensity, the so-called PMI metric, which is summarized on the next slide. The process mass intensity, one way I sort of think about this is it's kind of a little bit different from the E factor. If you remember, what the E factor looked at was the actual total amount of waste you generate divided by the amount of product you make. What this does is it kind of turns it a little bit on its head, and what it sort of looks at is how much material do you put in, quantity of raw materials you put in divided by the quantity of bulk material you get out. So whereas an ideal E factor is going to be the number 0 because you want to generate no waste, the ideal process mass intensity is going to be the number 1, whereas basically everything you put in comes out as product. Okay, just the definitions of this equation here. Process is all the steps of a synthetic path from commonly available materials to the final bulk active pharmaceutical ingredient, the API. Raw materials are all the materials you use, including water, solvents that are used directly in the process of not just synthesizing, but isolating and purifying the final API. And the bulk API out is the final form of the active ingredient that was produced in the synthesis, dried to the expected specification. The next slide is actually going to have a little bit of redundancy in terms of it's going to revisit a slide where we talked about why metrics, but why do we want to measure PMI? We want to have a number to help us drive towards more sustainable manufacturing processes, to be able to track our environmental manufacturing footprint and measure our process intensity. Importantly, we can track PMI throughout a process as a compound comes out of medchem into development towards a commercial synthesis. We're able to quantify improvements in the synthesis as we go. It's also an opportunity to be transparent. It's a common metric, so you have a basis for objective comparison, not just here at Pfizer, but across all the companies, the Pharmaceutical Roundtable. And it enables us to sort of benchmark, to have a simple comparison to ongoing green efforts throughout the industry to make us more efficient in our chemical processes. Okay. We have a tool for this. It's a PMI Calculator tool, and it's shown on this slide here, and it's readily available on the website I introduced earlier, the Pharmaceutical Roundtable website. What it is basically an Excel spreadsheet shown here, in which what you need to do is sort of have an idea of what your yield is and how much materials you're entering for each step of the synthesis. It's a spreadsheet. It has embedded calculations in. You fill in the amounts of reagents, solvents, and the aqueous, and then what the spreadsheet will do, it will calculate the step and overall PMI for your linear sequences. What it'll do is it'll do each step at a time, and then it will put the whole PMI for the whole synthesis together for you. And what it will also do is enable you to see the process mass intensity for the sequence, and also do a sort of a deeper dive into what impact both water, solvents, and reagents are having on that. So you can actually sort of see where you have opportunities to sort of drive improvements as you move towards commercial manufacturing route to your API. An example of API calculations is sort of shown here on the next slide. I'm sorry, I apologize. I chose an example from Pfizer. This is Viagra sildenafil citrate shown here. And what this shows is how the PMI changes over the life cycle of the compound synthesis. So basically on the left-hand side, you see the huge bar, the initial medicinal chemistry synthesis, where you have a PMI of over 17,000, which is not impressive. Once you optimize that in terms of going into development, phase 1, phase 2 manufacture, you see that number driving down significantly. And then when you get to a commercial route for this compound, you have a PMI of about 60. which is actually pretty good based in the pharmaceutical industry. What you'll see is if you actually look at the paper, specifically the green chemistry paper in 2015 from Pete Dunn and co-workers at Pfizer, you'll see that were the major drivers in terms of driving this, pushing this number down is in solvent savings. Optimizing solvents, reducing solvent use, and sort of telescoping crude compound through various steps enables this number to be driven down. One thing I will say is usually when people do comparisons on the medicinal chemistry route, it tends to be a little bit unfair because those routes tend to be developed for analoging, making the compound. Optimal purifications tend to be through chromatography because delivery of the compound in an efficient manner is the driver there, as opposed to the most efficient route to make the compound. So this is an entirely expected trend you'll see for the synthesis of most APIs. Okay. The synthesis of Viagra is a linear synthesis. It's basically 4 or 5 steps from a readily available pyrazole intermediate. However, not all syntheses are linear. You often have sort of convergent syntheses. And this is kind of shown on the slide here, where you have a number of branch points towards common intermediates, which are then combined to give you your PMI. So basically what we wanted to do there is sort of say, well, our initial PMI calculator doesn't give you the opportunity to build convergent syntheses, to build in for the synthesis of the start materials through these branch points. So can we develop a convergent PMI calculator which maintains the simplicity and calculation behind the original PMI while allowing a convergent synthesis for a range of complexities to be accommodated? And this was something that we did, which is sort of shown on the next slide. Convergent PMI tool, it's absolutely very similar. What you have is shown on the top right hand side. You have a bunch of tabs at the bottom of your Excel spreadsheet, and what those bunch of tabs enable you to do is go into a sort of linear sequence for the synthesis of each fragment. You're allowed up to 11 steps for the synthesis of each fragment. You're allowed 3 branches for a convergent synthesis, and then you're allowed 11 steps again to bring the multiple branch points together to give you your final API. So basically, you know, if you have a very long synthesis here, and trust me, molecules in the pharmaceutical industry are getting more and more complex by the day, you have the opportunity to calculate for a 44-step linear sequence with these various branch points if you so desire. However, the 2 tools I've explained so far on the PMI are actually kind of retrospective. What they do is they provide you an assessment of the greenness of your process after the synthesis. So really what you want to sort of be able to empower people is to sort of have an opportunity to say, okay, this is how I want to make my molecule. How green will my synthesis kind of look if I follow this synthetic route? And this is why in the last year or so we developed and rolled out a PMI Prediction Tool, which is sort of available from the website as an app. The goal of this tool is to provide a quantitative method to predict potential efficiency. The reason you kind of want to do this is throughout the industry, as I sort of just mentioned, there's increased molecular complexity, which leads to increased synthetic complexity. And as a result of that, the possible number of approaches you have to access a target molecule sort of rises exponentially. There's so many now, it's like molecular Lego. How many ways am I going to put this molecule together? And whereas you might sort of have a number of ways that you can write down on paper, the actual opportunity to go into the lab and experiment and sort of look at opportunities to be more green or more sustainable to synthesis sort of goes down. So you want to have a tool where you can actually look at it on paper and then get some sort of evaluation of sort of what the process will look like if you actually go and execute it on the lab. In the lab. So this tool sort of enables you to predict the range of probable process efficiencies for proposed synthetic routes at various phases of drug development. The key way that it does this is basically over time, the industry or the organic synthesis has built up a degree of historical knowledge on a number of specific reaction types. So what the team here did was went away, looked at chemistry that had been done on greater than a kilogram scale, and looked at sort of those various sort of type of reactions and looked at what a historical PMI for that type of reaction looked like, and also looked at the yield details of that. So you can actually plug in what those numbers kind of look like based on historical averages, and also use predictive analytics to estimate probable PMI ranges. What this enables you to do is a range of paper chemistry and be able to assess and compare potential route changes on paper prior to going into the laboratory. The next tool shows you a couple of screenshots and sort of shows you the sort of the workflow of how you do this. In the middle here, we talked about a convergent synthetic route. This sort of shows how you put your synthesis together. The first box, you define your synthesis tree and the stoichiometry of the reaction shown here. The second step is you define the reaction PMI. You can sort of see the boxes here. They sort of suggest what type of your reaction are you running, and then the app goes and sort of finds the historical data of reactions that have previously been run of that type and what the PMI kind of looked like. Box 3 shown here then gives you sort of an estimate, depending on what your yield ranges are, of what your cumulative PMI will look like for your synthetic step, for your synthetic route as a whole. And then box 4 does a breakdown by step. So you got to look at each step, where your optimal steps are, where you have the most room for improvement in terms of getting a better synthetic process. So it's really nice sort of developing this tool, but one of the nice advantages of developing it is you actually have real data to benchmark it against. So what the team did is they went away and they looked at sort of 15 case studies. 3 are presented on this slide. They had the actual cumulative PMI shown here in the first column, and then they were able to get a predicted cumulative PI and the 95% confidence interval shown in the brackets below in the boxes here for a number of sort of, as I say, pharmaceutical intermediates. One thing they also showed was the fact that they also looked at what the company was, what the drug was, and what stage of development it was, which was kind of one of the most interesting findings from this study. What you'll see is in this here, the actual predicted PMIs correlate pretty nicely with the actual PMIs. And what they also found was the accuracy of the prediction was dependent on the development states of the compound. Compounds in early stage of development, the predicted tool tended, the early tool tended to predict higher for those compounds as opposed to what the actual PMI looked like. Okay. It's very nice talking about PMI, but a couple of things just to follow up with. One of the things is the PMI actually does track with, environmental impacts as shown on this slide here. The left-hand plot shows tracking with the y-axis being PMI, the x-axis being global warming potential in terms of the kilogram CO2 equivalents generated. And as you can see, there's a pretty nice correlation. And the one on the right shows the tracking of a PMI against aqueous mass intensity. Probably a more interest to the industry. It's the next slide, which shows that lowering the PMI, now shown on the x-axis, drives down the cost per kilogram of your API. And there's a couple of studies in this space. I think this study came from Merck, and there's also a study out there from BMS, which shows a very, very similar trend. Okay. Changing gears a little bit and now moving on to solvent selection. I've shown you kind of how important solvents are in terms of how much they're sort of used in the industry, particularly in terms of like over 50% of your process mass intensity is based in solvents. Solvents, critical parameters in chemical processing for a number of reasons: promoting your chemistry, control the reaction temperature, dissolving your reactants, enabling you to remove impurities and byproducts of partitioning, and isolating your products. Choosing the right solvent could be your absolute key decision. A couple of things that people always say is, one is, why don't you run more chemistry neat? This is kind of a tricky proposition, because control of reaction chemistry in terms of the solvent acting as a heat sink is critical towards the safety of a chemical reaction. So that's one of the reasons. Another thing that's very emerging, is popular right now, is running your chemical processes in water, or promoting chemistry with the use of surfactants in water. And whereas this looks like being a great technology going forward, one thing to sort of consider is you have to look at the fact that the water has had organic chemicals in, so disposal of the water becomes an issue, and often isolation of your product from the water involves a chemical solvent because you need to do an extraction. Okay. A number of solvent guides have been sort of promoted, and what the various themes behind all the ones that are promoted, and we'll see a couple of examples on the next slide, is these 3 things carried out on this slide here. The first one, the most important, is obviously worker safety, the carcinogenicity, mutagenicity, toxicity, etc. of known about a solvent, obviously found on the material safety data sheet which comes with the solvent. The second thing to bear in mind is the process safety, the flammability, the flash point, potential for high emissions through a high vapor pressure, a static charge, potential for peroxide formation, and obviously odor issues. And the final thing, which is taken into consideration for the development of a lot of solvent guides, is environmental and regulatory considerations, such as ecotoxicity, potential EHS regulatory restrictions, ozone depletion potential, etc. I said there was a number of solvent guides out there, and there was a time when pretty much every company really had to have one. And a couple of examples are kind of shown on this page here. The one on the left is actually from Pfizer. It's actually you know, we had a magnet made of this. You'll see it all over the place at our sites. And it's a very simple sort of traffic light representation, green, amber, and red, going preferred, usable, and undesirable. It's pretty simple to see, but what's actually nice about this guide is there is actually a second part to it in terms of where you have undesirable solvents, suggested alternatives are provided. The one on the right is the result of some great work by the group at GSK, where they do a sort of a deeper dive in terms of separating the solvents into their various sort of functional group categories. You'll see alcohols at the top, et cetera, et cetera. And what they do is they do a deeper breakdown in terms of each of those sort of worker safety, environmental, human health, and show you where the solvent is impacting in a scorecard kind of fashion, each of those factors. Not to forget AZ, the Roundtable itself, Sanofi also published Solvent Guides, and as a summary of all of these in a green chemistry article in 2014. A more interesting one is actually also available on our website, which is the result of the Chem 21 initiative in Europe a couple of years ago. This is actually a great educational resource on the website, because also behind this solvent tool, there's also a number of exercises in terms of, you know, digging deeper into why the solvents are issues. They choose 77 solvents, and they do ranking again based on health, safety, and environmental criteria, and also look at about the physical property data behind it. Basically what they do is they sort of do the rankings by default, and again, similar to that sort of preferred, not preferred, don't use kind of category, they look at recommended, problematic, or hazardous kind of rating to sort of, you know, guide your solvent selection. So we looked at solvent selection guides, but as a chemist in the lab, what do we actually sort of do in terms of when we actually have to choose a solvent? Guides are pretty good. They offer you assistance in identifying solvents. However, again, it's like the PMI tool. It sort of offers a sort of post-selection comparison between solvent options. Basically, objective solvent decisions for comparison are compromised because, you know, I go into the lab and basically I'll sort of look, what do I have in the lab solvent cupboard? Or also, you know, what's my personal favorite solvent? What did I do last time? What did the guy who did this reaction in the literature use? Or then also similarly, what other similar solvents are commercially available? So basically, you know, when you sort of look at choosing your solvent, the choice is restricted by your simple consideration of the chemistry. If a solvent's going to be incompatible with the chemistry you're going to do, you don't want to use it. If you need, you know, to reflux your reaction, the solvent you choose is going to be based on the boiling point of that solvent in terms of getting the temperature range you want. And also, there's many cases, particularly with the dipolar aprotic solvents, where these are the best solvents based on their polarity for the reaction you want to do. So the type of chemistry guides you to choose a solvent. What we wanted to sort of do was look at sort of a more holistic way to choose solvents, and look at developing a solvent selection tool to reverse this philosophy and look at a more proactive approach to choosing a solvent for a specific reaction. This sort of tool is introduced on the next slide on the right hand side, and this tool incorporates 272 solvents in a data set. And what it does is the selection is actually based on molecular physical properties, EHS criteria, environmental health and safety, various ICH guidelines, over 100 properties. And what it does is it uses statistical analysis to break these properties down and analyze them through principal component analysis. And this tool is an interactive, adjustable visualization with a screenshot shown on the right-hand side. What you see on the, to go back a slide. Could we go back?
I think you should be able to go back.
Can we go back a slide, Natalie?
Yep, I think you have control to go back a slide.
Okay. What basically the tool shows you is each of the spots on these two visualizations shown here represents a specific solvent, with the X and Y axis looking at principal components, which you sort of describes a group of molecular properties of those solvents. On the top, you'll have a filtering bar shown here as functional groups, where you're able to actually filter out a solvent based on it's sort of what type of solvent it is. So you can sort of look at all the alcohols at once. But what I find, you know, specifically powerful about these tools is as you actually look at this straight on, when you have all your solvents in front of you, 272 solvents, you know nothing about the identity of what any of these solvents here are. So basically what you're actually doing is you're going in kind of blind and trying to look and making a decision about what solvents might work for my chemistry, what solvent should I use sort of to evaluate to see if they'll work for this kind of chemistry. So basically, this sort of slide here shows sort of two kind of uses for this tool. On the left, we sort of have a sort of an optimization sort of setup kind of thing, and on the right, we sort of see on the left, we sort of see an opportunity where you can screen specific solvents, and on the right, you see a sort of opportunity where you can optimize a solvent for a specific transformation. As I say, the left-hand one looks at optimization. You're going in, you have a specific reaction, you don't want to know which solvent to use. You can look at doing applying a specific set of filters to look at a short list of potential solvents. As I say, it will then flag up specific solvents circled in red here, which give you an opportunity to have a starting point of what solvents to look at for the reaction you're going to evaluate. On the right-hand side, it's a kind of a different kind of setting. Here, you actually have an initial hit for your chemistry. You have a solvent you're working on. You want to look at different solvents. The thinking behind here is if your solvent is part of this cluster highlighted here, solvents around this cluster also highlighted it's reasonable to expect that they should have some sort of similar physical properties and might be better solvents to evaluate based on their sort of physical properties. Okay, moving on to the final tool now, we looked at development of a reagent guide. For a reagent guide, what you want is you want to have three ideal characteristics. You want to provide a balanced assessment of chemical methods. You want to have an ability to work in good yield in a wide variety of drug-like molecules. You want to have wide scope of a chemical transformation. You want it to be able to be utilized for scale-up purposes, and obviously we want it to be as green as possible. The other things behind the guide is you want to have easy access to the chemical literature. You want to sort of have it based on chemical precedents and it be able to guide the sort of user of the guide to the sort of reference points where they can find out more details about a specific transformation. And you also, of course, want to raise awareness of newer emerging greener methodologies. As I say, you can find the reagent guide from our website. This is what the front page looks like. There's basically a range of transformations shown there, and you can select them as you go. I think we're over 20 at this point. We're going to talk about oxidation to aldehyde and ketones today, but all the sort of reactions we're sort of evaluating are shown on the right-hand side, and we have 7 more guides coming this year based on the transformation shown at the bottom here. Basically, when you sort of hit on the guide, you'll get an introduction to the transformation. It'll tell you general reviews on that kind of chemistry. But the most useful thing I find from looking at this guide is the sort of Venn diagram visualization, which we're showing here, which I'll sort of walk you through briefly. Basically, the Venn diagram is split into three boxes, 3 circles shown here. The top left, you have reagents. The top left circle highlights reagents that are widely utilized for the specific transformation you're looking at. If you want something to work or you want a high chance of a reaction working, this is where you'd sort of be looking. This is sort of the very popular area in terms of the sort of medicinal chemistry area. On the right-hand side, the right circle, you have scalability. Reactions that have been demonstrated on scale previously under these kind of conditions, and they're seen to be easy to scale up. And down the bottom circle, what you'll find is reactions or technologies or protocols which are green chemistry aligned. The reagents are green in terms of safe, the less waste generated by those kind of things. And this is sort of the area we want to try and encourage people to use. However, what you'll also find is there are interacting circles here. So obviously, for whatever you want to be, the ideal place to be is right in the middle. That's where you have a reagent or a sort of protocol for doing a specific reaction, which is widely sort of has great utility, is easy to scale up, and is also green. What you have here is when all these sort of reagent combinations are hyperlinked, if you click on them, it brings you into a deeper dive about that actual sort of set of conditions, including the mechanism, comments about the sort of, the implications of using that kind of thing. It sort of gives references, it gives scale-up examples, and also provides a sort of a green review. And this is sort of not based on it's not green or it's green, so some sort of holistic sort of viewpoint. It's based on actual fact in terms of, in case say like using DMSO or the Swern oxidation, it'll tell you there's odor associated with it. It will tell you there's a sort of a dichloromethane is often used as a solvent. Dichloromethane is not a preferred solvent. Okay, Looking at sort of a real example of this, and this is a synthesis of the HIV compound Maraviroc. You look at this sort of this alcohol oxidation shown here, the first generation synthesis. We see some sulfur trioxide and pyridine was used. Again, we see methylene chloride, not a preferred solvent. We see dimethyl sulfide with a stench is generated. This is kind of a typical medchem route. It's a great yield. It's a widely applicable synthesis, and these conditions were sort of in that upper left corner. As you see then, when you go into a second generation synthesis, we're moving into sort of a tempo radical generated oxidation, now using bleach as the stoichiometric oxidant for the transformation. Again, it's not ideal. You've got methylene chloride as a solvent, but what you have here is you have sort of environmentally benign byproducts, specifically water and sodium chloride shown here. And then later development shows that you can replace the undesirable solvent with methylene chloride with ethyl acetate, which is a greener solvent. And this is an example which is provided in a reagent guide. And as you can see, it's been done on a pretty decent scale in terms of multi-kilograms. As I say, the green review is based on sort of quantitative, real information based on atom efficiency, safety, toxicity and environmental impact, and cost availability and sustainability of the feedstocks and long-term sustainable implications. Okay, so that summarizes the reagent guide. I'd like to thank everybody for attending today. I'd like to thank my fellow member companies, the Roundtable. As you could say, see there's quite a few of us now. I think there's 34 member companies. If we get any more, we'll probably have to get a new slide. I'd also like to thank these individuals specifically on the right-hand side, Alina, Christiana, Amy, Luis, Isamir, and Natalie for their help today. And I'd be delighted to try and help answer any questions if anybody has any. Thank you.
Awesome, Paul. That was great. A great introduction to all the tools you have available. So just to start off, are these tools free of charge and anyone can access them by going to that link that you provided for us?
Hello?
Oh, Paul? Paul, that was a great presentation. Can you hear me?
And Natalie, I can't hear you.
Oh. Can you hear me now, Paul? Can you hear me now, Paul? Ishmael, can you hear me and see the questions to read to Paul?
I can hear you.
Oh, there we go. Great. I'm sorry there. We must have had a connection issue going on. Paul, that was a great presentation. I really appreciate the time that you took to put that together. I do see some questions coming into the chat box, so I'm going to start off with that.
Hello?
Paul, can you hear me? All right, looks like we're having some connection issues with Paul. Paul, can you hear us? Ishmael, I can hear you, so can you hear me?
I can hear you.
I'm not sure why Paul can't hear us, so geez.
Hello?
But,
Oh,
Paul, can you read the questions?
I can hear you now.
Great. So the questions that I see in here are, what goes into the scalability metric? Is it possible to find out why one reagent was considered scalable or not scalable? And that question is coming in about your metrics from the very beginning.
Is that I sort of see that more in the sort of reagent guide space as well, in terms of that is a concept there in terms of how reagents are binned, the scalability. A number of factors come into scalability. One thing with the reagent guide is a lot of it is based on historical sort of things in terms of examples. When you actually sort of evaluate whether you can scale chemistry up, safety is obviously the absolute critical thing around the use of a reagent. So safety is a key consideration. Greenness is always in there. Atom economy. What the Roundtable also contribute to is there's a review we put out there in terms of it's just been updated last year in terms of key research areas where we highlight chemistries where we believe the chemistry is not optimal. You can, I think I mentioned during the webinar, the Mitsunobu reaction, which is chemistry that you can't scale, but from an atom economy standpoint, it's not ideal. The other things in terms of scalability is often, obviously the solvents you kind of use for the chemistry. The downstream processing becomes a key consideration as well in terms of how you actually work the chemistry up. So there's a number of elements that go into it.
Great. And so I think one question that maybe you didn't hear was, so are these tools free of charge to anyone, or is it specifically to the Pharmaceutical Roundtable?
The tools are absolutely free of charge. You can get to them from our website. For a while, the reagent guide had a login to it, but it was still free to register to use. But I believe that login's been taken away. We were very sort of upfront in terms of when we were developing them. We wanted sort of key into, I also mentioned we want to sort of inform a research agenda. So we really felt that we wanted something to be openly, openly available, and also, educational as well. Specifically when you sort of look at things like that, if you saw when I was talking about the Solvent Selection tool, you might have seen that basically that had that kind of interactive visualization panel where you could click on dots and filter, etc. The decisions behind what sort of software or platforms we used were also built into making them publicly available in terms of what sort of tools we had behind, what sort of software we used behind the tools. But one thing I sort of say, people ask about them is, I'd openly encourage people to go in and use them and give them a try. It's easy to listen to someone talk about them, but there's no substitute for giving them a go.
Yes, I would definitely say that's definitely true. And I know that we have one of our green chemistry commitment signers, Professor Dalia Kovas from Grand Valley State, actually brings this PMI tool into her green chemistry and environmental course. She was here with us on the webinar, also talking about how important those solvent selection guides are. But she utilizes this tool in her course and has them look at a greener and a traditional synthesis, and uses that PMI tool to do that. So it's already being brought into classrooms, and we encourage other people to do the same.
Oh, that's absolutely phenomenal to hear as well. And we talked about the example of sort of driving the metrics down in terms of PMI, and we had the Viagra example. I feel when you combine the tool with the actual chemistry behind it and sort of dig into where those improvements are made. I think we talked about solvent savings. I think it becomes a very powerful message on a number of fronts.
Yes. So we have another one coming in that says, thank you for a great presentation. My question is, how much consideration could we give to the bio-based solvents in the solvent selection procedure?
That's actually a great question in terms of bio-based solvent. I think maybe it was a little too honest when I sort of went into, as a scientist, what you actually look at sort of when you were actually evaluating solvents. And if there is a sort of a downfall in terms of the typical solvent selection guides, is that they're based on a number of criteria, and what you're sort of relying on is you're relying on the knowledge behind them being readily available. And there's a lot of interest in bio-based solvents are in this space in terms of new emerging solvents, and you get into a sort of catch-22 situation of when a solvent is new, it's not readily available, and then it becomes less of a sort of an option to be utilized at an early stage. So it's, I say, catch-22, chicken and egg. You want to use the solvent to get increased usage to get it more readily available. What I will say is the Solvent Selection tool, and I probably didn't highlight this very well, has a sort of a number of tabs across the top. The one that was highlighted, the filter that was highlighted in the top left-hand corner was on functional groups. One of the tabs across the top is actually an environmental health and safety tab, which enables you to sort of filter to sort of look at bio-based solvents or things that are from a sort of more renewable standpoint. The other nice thing about the Solvent Selection tool, as I say, rather than it being a more proactive approach to selecting a solvent, is there's a lot of solvents in there. It enables you to consider, as I say, there's 270 odd in there. It enables you to consider sort of more emerging solvents. And you might say, well, you know, you might not have all the physical property or all the environmental data on the solvents, but there's a lot of sort of things where data is not known. There's an opportunity to sort of calculate it or estimate it based on, you know, what's known about closely related solvents. I think that's somewhat of an issue in solvent replacement, is people will sort of say, oh, you know, I can't use this variant, and they'll introduce a sort of a homologue of a certain solvent, and because the toxicity data for that or the environmental data is not available for the homologue, there might be the assumption, oh well, that's a greener replacement, when in reality the data is not known. But that's a fabulous question.
Great. So there's another question that we have here about solvents, and it says, for the solvent selection tool, it looks like a lot of the solvents are missing the SHE, so SHE data points. Is there interest in adding more health and environmental info to the tools where data is currently missing?
Absolutely. No, I think that's key, and I think that's something where the Pharma Roundtable have been pretty proactive in it. Not in terms of when I think the example I always use is there's a big need, particularly with the emerging REACH legislation, to I guess outlaw certain solvents, and I mentioned the dipolar A protics, which are actually great for nucleophilic substitution chemistry. But I think there's sort of, you have a NMP and methylprodone, and then people say, well, the butyl variant is not toxic. A lot of the thing there is sort of that data is not known. So adding, you know, having a number of companies interested in enables to sort of to share the sort of, for want of a better word, burden of sort of assaying that compound in the toxicity assays and getting real data to incorporate into these tools. One thing I didn't say, and I ended on the Reagent guide, which is probably the best example to say, is these tools are sort of living guides. You know, it's like when you drive a new car off the lot, it immediately loses 30% of its value. When you put a Reagent guide together, somebody comes up with a new way to do a transformation, so it's kind of already out of date. So with regard to adding the EHS, the SHE data, that's an ongoing endeavor to update the Solvent Guide. Similarly with the Reagent Guide, we try and encourage people to, if you see an interesting transformation that we'd like to be included, you know, just let us know. There's like a feedback box on a number of these tools.
Great. So in line with that, there's a question of, are the tools integrated? So are ROHS and REACH integrated into the tools in any way?
REACH is definitely integrated, particularly into the Solvent Selection Chem 21 tool that emerged out of a consortium in Europe. Where they put a lot of money into sort of green technologies, and this, which the Roundtable sort of kind of inherited or was part of. The REACH is, and I think specifically it's into that, when I sort of went through the ratings of the solvents, like, you know, usable, problematic, you know, hazardous, I believe the REACH is taken into account in terms of problematic, and the reason behind that is it's sort of, you may have issues down the road in using the solvent, so better to be aware of that right now and sort of, you know, make a contingency plan from the outset. But that's a great question.
Great, and I think the point of highlighting these tools in the discussion we're having today is to really make sure that these make it into the educational system, right? So we're even thinking about it from that point and going into the industry you may end up in the future, that you want to be thinking about scalability and waste and all of these things that you've talked about today, Paul.
Sorry, I totally agree, and I think the nice thing is that the tools are promoting green practices, but, you know, and I look at the Reagent Guide tool, they're also great from a, you know, synthetic chemistry perspective as well, in terms of, you look at the background, you can learn about mechanisms, and they don't just promote the green options, they try and do it in a sort of a a fair assessment kind of manner. There's green options, but this is other options, and this is why they're considered not to be green, or this is the problems you may have with them.
Great.
And I would like to add that we're going to roll a new a new version of the Solvent interactive tool this week. So I think that by Thursday, Friday, I believe it's Thursday, tomorrow, we're going to have a new version. I might have more information about the EHS data points that it was mentioned in one of the questions.
Awesome.
Super.
Yeah, awesome. We got the inside scoop here from the ACS. Great.
It's coming.
It's coming. Great. So we thank you all for joining us today. Paul, that was a wonderful presentation and giving us the insight onto the tools. I just want to announce quickly, the Green Chemistry Swag giveaway winner is John Williams. I will be in contact with you to hear your selection from our choices here. Thank you so much for joining us. The recording will be sent out tomorrow. We thank the ACS GCI Pharmaceutical Roundtable for their time. Thank you for listening to our webinar, and the recording and supporting documents will be posted on our website. You can sign up for our mailing list on our homepage at www.beyondbenign.org for notifications for upcoming webinars. And our next webinar will be in February, so we will see you back here then.
Super.
Thank you.
Thank you.